All right, hello and welcome. In this video, we're going to look at how to calculate our total inductance in this parallel circuit here. And then we're going to measure our impedance and use that measurement to verify if it's accurate by calculating the inductance from it. Okay, so in this case here, we see that this is a parallel circuit. We have no choice but to go down each branch independently. And so that is L1 in parallel with L2 in parallel with L3. They're all in millihenries, and so we're going to write that into our parallel equation just like we do with resistors. 1 over 1 over. And then we'll put our first inductor on the bottom, 14. We'll leave it out of the millihenry range because they're all in millihenries, so we know our answer is in millihenries. Plus 1 over 28. And plus 1 over 8. And that gives us our millihenry output. So we'll write that down as our LT, our total inductance. So LT is equal to 4.31 millihenries. Okay, so now we can measure our total impedance in the circuit. And so that is done using our LabVIEW icon. So you can go over to the sidebar on the right here and click on the drop down and get your second meter out there, and that is the impedance meter. Or you can go up to the Simulate tab, into Instruments, down to LabVIEW Instruments, and get your impedance meter off of that as well. So we'll place this over here and we'll plug it in where we expect our battery to be. So the positive goes on the top line, the negative goes on the bottom line, and this is going to induce a frequency through these inductors here. And there's actually a problem with this. When we double click on this and initially play it, it won't give us any readings. Right? And it actually sends some errors out. It says that it can't do it because there's some kind of short in the circuit. And that's because these are inductors and essentially they are shorts. Right? So now we have to add in a few resistors to be able to make up for that. And so we'll just grab a resistor out, any resistor, we'll okay that, and we can place it directly on that line as long as our circuit is not currently running. So make sure your circuit's stopped. We'll place that on the line there. We'll place a second one on the line right after that, and we'll close this out. And we don't want these to be this big of a resistance, so we're going to double click on these, and we're going to make them really, really small, 0.001 ohms. Right? Really, really small resistances. We don't want them to impact the circuit. We just need our meters to be able to measure our parallel branches, and this is the only way it's going to be able to do that. Right? Otherwise, it's just going to short everything down through L1 and move on, and it's not going to send anything through L2 and L3 because L1 is a short. Right? But now it has a reason to draw current down through R1 down through L2 and down through R2 to go down through L3. And so that's why that is needed. So when we double click on this again, we can now hit play on it and get values out. And we can calculate using these values. So we have multiple values here. We've got our frequency at the beginning here. We're going to use that in our XL equation. We do have a very, very small resistance being shown here. That's because we put the resistors in here. Usually this number is even smaller than this. In our series circuit, we saw that. Our inductive reactance is right here. That's 1.623. And so we're going to use that to calculate. That's our impedance in our circuit, inductive reactance impedance. It's in ohms. And then we also have our Z value here, and we see that these two match. And that's because we actually don't have enough resistance in the circuit to make this get any larger. We don't have any capacitors in the circuit. So once you have capacitors and inductors and resistors, look at Z. Otherwise, grab X because we're looking at inductors. Let's grab our formula out. So we'll get this question mark here. That's going to tell us our formula. XL equals 2 pi FL is what we're going to plug in. We're going to solve for L out of that because we just got XL. So we'll rearrange that. So 1.62 is our output here, ohms. So XL is equal to 1.62 ohms. And we can use that in our inductance equation. So we'll say that XL is also equal to 2 pi. That's our circle, F, the speed of our circle, and then our LT. So we're going to solve for LT out of this equation here. So let's plug in. We'll say that we know that it's 1.62 ohms is equal to 2 pi, our 60 frequency from our meter, and then we'll write LT at the end. We'll solve for LT by dividing out 2 pi times 60 to both sides. 2 pi times 60. Right? And so then we can say that LT is equal to, and we'll solve for that. We'll send this out so that we have 1.62 divided by 2 pi times 60. We get that small number out, so we'll write that in here. We have 0.004297, and that is in henries now. So we want to move that into millihenries so we can match it. So we'll move it 1, 2, 3 back, and we see that we have an LT value equal to 4.3 millihenries. All right, let me know if you have more questions.